Welcome back to Computer Science 3200. As you can see by the schedule here, we're on Lecture 2 because it is Tuesday, and today we're going to be going over agents and environments. Just a quick note about Thursday's lecture, so the next lecture 2 days from now. That lecture is going to be long. It's going to go over time. The reason that it's going to go over time is that you can see here I'm doing a whole lecture, and then I'm introducing assignment 1. And unfortunately, since this class is on Tuesdays and Thursdays, releasing an assignment on a Thursday instead of on a Tuesday gives you 5 extra days to work on the assignment. And that really starts to add up over the course of the term. So Thursday's lecture will go over time probably by quite a bit. But in order to make up for that, the following Tuesday is not going to be a lecture. It's going to be 100% devoted to assignment help and a big tutorial on the assignment and how to do that and how it works and going in depth through all the code. So Thursday's lecture and stream will go long. However, I'll sort of make up for that by giving the next lecture after that is entirely devoted to extra help with the assignment. So please forgive me that one's going to be long. You can watch it at your own pace. However, the assignment will be released on Thursday. And as a reminder to people who are watching this who are not in the course, the assignment files are not released to anyone outside the course. Only registered students in the course get assignments. And the way you are going to get your assignment, because a few people have been asking me, where are the assignments, is that you are going to get an email by Thursday, probably sometime tomorrow, with links to download the assignments. And all of the assignments are completely individualized to you, and I'll go over that a little bit more in the next lecture. So let's get started here with today's lecture. And today's lecture is all about the start of the story of artificial intelligence and how we study it in academia. So if you were going to, go build a house somewhere, you've got to lay the foundation, right? You've got to have a good foundation before you start building all the rooms and all the fun stuff in the house. And if your foundation sucks, then your house is going to collapse. And so this is one of those foundation lectures where it's going to be a lot of definitions, a lot of examples, a lot of terminology, but you need that in order to go forward and actually understand what you're talking about. So we've got to establish this common vernacular, if you will, so that we can talk about artificial intelligence going through the rest of the course. So this lecture is going to be pretty dense in terms of new terminology and stuff. However, I think it's completely understandable, and I've got lots of examples, and so that's what we're going to do today. So let's start. So lecture 2, agents, actions, and environments. So a quick note, this is the most dense lecture of the course in terms of definitions and terminology. So don't worry if you're a little bit lost in your first viewing. You can always go back and watch stuff. And important concepts that are in this lecture will be reiterated in later slides, and you'll come to be quite familiar with them. And you can use these slides as a reference going forward for the rest of the course. And just as a quick note for students in the course, probably several questions on the exam will be from this lecture, okay? So almost anything in this lecture is directly testable. So if you're going to rewatch any lecture, rewatch this one. Someone just had a question there in the chat. Do you upload your PDF lecture files before the lecture? No, I don't upload them before because sometimes I spot errors in the slides and I make changes to them during the lecture, and then I upload them immediately after the lecture. Okay, so that's how the slides are done, just in case I find any mistakes. All right, so what is an agent? Well, an agent exists in a specific environment, right? So I am an agent, Dave is an agent, and the environment is the real world. The agent is the entity for which we want to make decisions and take actions. So really, the entire point of artificial intelligence is to come up with a system that makes decisions in some way, okay? And those decisions are going to be the basis for actions that you take in an environment. In most cases, the environment defines a problem while the agent gives a solution. Okay, so the environment is going to be like a pathfinding or video game environment, or maybe it's outside if you're trying to make a lawn mowing agent or something like that. So the problem is contained within the environment, and the agent is the solution to that problem. And there are many, many types of agents. So here, for example, your problem might be my house is dirty, right? So a potential solution to that problem is a Roomba. So the Roomba is the agent in this case here. You see it going around trying to clean the room. In another case, you might have, here we have Boston Dynamics dog called Spot. It's a robotic dog. And in that case, the agent is Spot, right? So here it is trying to open a door and move around the facility. We may have simpler agents. So for example, here we have a problem that's a very sort of canonical problem in AI. It's called the balance cart. And in this environment, the point of the thing you're trying to solve is make this balance cart balance the beam upright for as long as possible. So what you can do here is you can move left and right in order to swing this pole in this physics simulation, and you want to try and balance it as much as possible, or as long as possible. So here the agent would be the balance cart. If you're talking about a game, like for example a board game like chess, then you may think that the agents are the pieces on the board, but that's not true. The agent here is the thing making the decision, so it's the player. So the player in charge of making those decisions, that is the agent in this case. And if you go on to something a little bit more complicated, like a video game, for example, then the agent is going to really depend on the problem. Like, for example, you might be trying to make Mario speed run a level, and in that case, the player or Mario is the agent. If you're trying to make good AI, for example, for the Goombas or the paratroopers or something like that, then the NPC would be the agent, right? So it depends. In more complicated environments, the agent may not be so obvious depending on the problem that you're trying to solve. So an agent within an environment will take actions to achieve some particular goal, right? So the agent in artificial intelligence, we always have to specify a goal that we want our system to achieve. And so the agent is trying to achieve a particular goal within an environment. What the agent is going to do in order to try and solve that goal is it's going to perceive its environment somehow and then make decisions about what action to take, right? So the perception, the agent's perception of the environment is critical. Like sometimes if you're playing a game of chess, you can see the entire environment. But if you're a self-driving car, maybe there's obstacles in your way, right? Maybe there's a tree and you can't see around the tree or something like that. So the perception is very important. The agent is going to make some decision, then it's going to take its actions, and those actions will change the environment somehow. And then this process is going to repeat and repeat. And so AI is the algorithmic discipline of making these decisions more intelligent. So now that we know a little bit more of the terminology, right? AI, and when we talk about more intelligent, and we'll get to this later in the lecture, but more intelligent means it's able to achieve its goal better. Whether that's faster or more points or whatever, it's able to do that better. So graphically, if we have this graphic here where we have environments up on top and agents, well, agents are going to take actions. They're going to make decisions and take actions. Those actions will influence the environment. Like, for example, an action might be picking up my phone and placing it down over here, right? So I'd move my phone from one side of my desk to another, or I could turn around, or I could jump, and all of that will have some effect on the environment in some way. Sometimes the effects are really big, sometimes they're negligible, but there will be an effect. And then the agent, after it takes its action, it's going to make a new observation of the environment. It's going to look around or get its data or whatever, or look at the state of the chessboard. And then it's going to make a new action, and then that's going to affect the environment. It's going to take a new observation, and the agent's going to take a new action. And so this is a cyclical thing that happens throughout the course of the agent's lifespan, whatever that may be. So, agents perceive their environment through sensors, right? So whether or not it's like a physical sensor, that's going to differ depending on the agent and the environment. But for example, maybe we have a robot, like a self-driving car, for example. That robot may have a camera that it can look at the world. It might have a laser for doing sort of distance range finding. It may have a sonar system. It may have a whole bunch of different sensors. Humans have at least 5 senses that we're aware of, right? So I'm not going to list them all out, but I can touch my microphone to make sure it's still here. I can look over and see OBS running with the recording to make sure that it's still there. So humans can perceive their environments with their sensors, and we have our senses for that. When it comes to things like video games, we may have the keyboard input, so sorry, that shouldn't be there, but it's going to perceive the game through some sort of game state. So for example, it might be able to read the RAM of the game and say, oh, look, in this array that represents the board, where is my player? Or where is this piece? Or Mario is at location X equals 20, Y equals 47, right? So it's going to be able to perceive the environment somehow. And then the agent is going to act on its environment through actuators. And so this is where this keyboard thing should have been. So robots are going to act with their wheels. So if it's a car, it's going to drive forward. It's going to apply a voltage to a motor. That motor is going to turn a wheel, etc. Maybe you have tracks. Maybe you can like pick up something and lay it down over here. Humans, obviously, we have limbs. We have tools that we can use. And in games, you're going to have some predefined rules or actions. Or if you're a player, maybe you click the mouse or you use the keyboard or the controller or something like that. And that is how you, as an agent, are going to act on the environment, which is the video game. And agents also, they may have some knowledge about the environment to start out, okay? For example, if I'm playing Mario, I know that Mario can jump on top of Goombas to kill them. That is knowledge. If I go outside, I know that a coat will make me warmer or something like that. The robot may know, for example, the street that it's going to drive down. It may know the directions, it may not know the directions, and so agents may have some knowledge about the environment, but they may not either. So I talked about this notion of perception, right? And so how does an agent actually look at the environment in order to make decisions? So a percept is the agent's perceptual inputs at any instant. Okay, so as a human, I guess you could do this like you keep your eyes closed and then you open them and you close them. And that's like a snapshot. Or if you take a photo, right? That is your input at any given instant. And so we sort of say that this is the agent's current belief of the world. And why we say the current belief of the world is because there may be some stochastic elements, like there might be chance. It may not know that there's something behind that tree. So it has to believe in some state of the world with a certain probability at a certain time. And we call that the environment's current state. Okay? So this is very important. The state of an environment is how the agent perceives it at any given instant in time. Okay? And as time goes by in our simulation or our experiment, the state of the environment is going to change as the agent looks at it. So, also keep in mind here that the actual physical, the actual environment may change, but the agent's perception of that environment may not change. So, for example, if the agent can only see, and something moves behind a tree, like I said before, the environment itself has changed, but the agent's belief of the state of the environment may not have changed, because it may not be able to see everything. And we'll get into those properties a bit later in the lecture. So then, if that's a percept, then a percept sequence is the complete history of everything the agent has perceived so far. Okay? So the percept sequence is kind of like the history of belief of the agent up until this point. So if I'm running down the road, maybe I saw a dog a few minutes ago, right? So that's not currently in my current view, but I do know that at some point a few minutes ago, a dog passed me. And so that's part of my percept sequence, is that there was a dog. All right. So in general, meaning that in the most complicated of cases, in general, an agent's choice of action at any given instant can depend on the entire percept sequence to date. And so what this means is the things that I saw in the past can matter for my current decision making. In general, that's true, right? In this course, we will really, going forward, we'll only be looking at problems where the current state is sufficient to decide. So this means we have fully observable states. So for example, we're not going to be dealing with hidden information or anything like that in this course. That's a whole other topic. And we're also not going to be dealing with problems where like the state history is required, right? So we're going to be dealing with more simple problems that we can apply the algorithms that we're learning in this course to. So the agent behavior is given by the agent function, and that's going to map a percept sequence to an action. And that's a lot of mumbo jumbo, but basically what it means is, given what I've seen so far, I'm going to take this action, right? And this agent function can be as simple or as complex as you want it to be. So that agent function could be a lookup table, right? If you're playing a game simple like tic-tac-toe, maybe you have like a big cheat sheet that says if the current state of the environment is this tic-tac-toe board, put an X here or put an O here, right? Or it might be something as complex as a neural network, right? A deep neural network with millions of weights and connections and stuff like that. So this agent function just means that's sort of the brain of the agent. And when it sees something, it's going to use its current knowledge and its current algorithm to take a given action. So what's an example where history may matter? Well, here's an example. So if this is a current state of the game, sorry, let me repeat that. If this is a percept of an agent, right? So this is a snapshot taken by an agent at a time step t. What do you think will happen 1 second later? Like, what will the state of the world be 1 second later? What do you think it will be? Can you describe that in the chat? Like, where will this person be 1 second later? I'll wait until I have... Okay, so someone says the water will have moved and the person will have fallen, right? Perfect example. So you as a human being, you're an agent in this environment, and this is what you've perceived at a given moment. However, you're not really sure of that, right? So some people are saying free fall into the water, further down. We're not entirely sure. Like, we have a knowledge of gravity, right, as humans. And so we're applying that knowledge to this situation. But maybe that person jumped from here. Maybe they jumped from here. Maybe they jumped from an airplane, right? So we don't necessarily know where they're going to be. We don't know their current trajectory. And so we don't know if there's a big trampoline down here and they're just doing a backflip and they're actually on the way up, right? And so the current view of an environment can be tricky. And in the most complex of cases, like for example, if you're a firefighter with a big blanket trying to catch this person, right, walking around, you do have to know more than just this snapshot. You need to know their speed, you need to know their angle, maybe the wind direction, stuff like that. So in the most complex of cases, the entire history is necessary to make the best action. Okay? So that's the most complex example, but we're going to deal with simpler examples, right? So can someone out there tell me, just type yes or no, if you believe, is the state history of a game of chess required in order to make the best possible decision at any given time? So that's a yes. Or no, I just need to look at the current state of the game in order to make the best possible decision in chess. Okay, so I've got like 10 no's out there already. That's great. So what that means is, even though it's a little bit counterintuitive at first, you might say something like, well, maybe I need to know the order in which the pieces were taken in order to make the best possible decision. But it turns out no. The order of moves in which you got to a particular chess location or a particular configuration of a chessboard doesn't matter. Now, I will say that with a little bit of a caveat, that chess does have this like repeated moves draw thing. So if you go back and forth, back and forth, back and forth some number of times, then the game will be a draw. So in that very particular edge case, you do need to know. And also for like castling, maybe I should have put a checkers board up here, right? So in checkers, there is absolutely no state history required. So yeah, that's what I'll do. I'll change this to a checkers board, but you get what I'm saying, right? You don't need to know the whole series of things to play chess. Here's an example from League of Legends. Now, this is a bit of an old example, but I do like it a lot. And so here's an example from LCS, I don't know, like season 3 or something. This is like old TSM versus Team Liquid. It was years and years ago, but I love this example. So here we've got the Baron. And so the Baron is this monster that if you kill it, and killing a monster in League of Legends, you need to do the last hit point of damage, okay? So whoever deals the last hit point to the monster effectively gets the rewards from killing that monster. And the rewards from this monster are a ton of gold. You get a buff that like makes your back go faster. You can you regen faster. It's really good. It's like completely swings the tide of the game to kill this. So here you see a team killing the Baron, and then Piglet from the other team just walks up and kills it, right? Easy enough. Like, why wouldn't he just come up and fire the rocket at the exact time that it takes to kill the Baron? Well, this is like the spectator's view of the whole game. Here is what Piglet saw. Okay? So he actually had no vision of the Baron. And so he would need the last minute or so of gameplay worth of information in order to fire that at the perfect time. Now, of course, not every time he makes this shot is he going to get it, but he needs to have that information of sort of, he has a bunch of game knowledge on like how much DPS all the characters can do, approximately how long it will take to kill them, and then when they arrived, maybe 30 seconds ago, when they started attacking, and so he makes this decision to fire at a particular time and got it right. So in these really complex examples, yes, the history of perceptions of the game do matter. However, for our assignments in this course, we won't be dealing with such complex states. Someone in the chat said the TSM agents need to be fixed. Yeah, exactly. Yeah, report the jungle didn't smite. Lots of memes we can talk about it. Well, let's move on. But that's just a good example of how you need the history in general. So an agent, actions. So what are actions then? So an action taken by an agent in a given state transitions the state into another state. So what does that mean? Well, let's take an example where I take my phone. I'm going to take the action of moving my phone to the left, right? And so that transitions the state from my phone being on my right. Well, my camera is a little bit mirrored. My phone being on my right to my phone being on my left. That is a transition from one state into another state. Now, you should all be familiar with what's this called? Does anyone know? What's this type of machine of finite size that deals with states is? Does anyone remember the name of that thing? So here's a state diagram of a finite state machine. Yeah, so this is a finite state machine in which we have two states, state 1 and state 2, okay? This is like the simplest possible way of representing an environment. Over here, we have the state transition table that represents the state transitions from actions. So what does this mean? The state transition table says if I'm in state S1 and I perform action 1, I stay in state S1. But if I perform action 0, I transition to state S2. If I'm in state S2 and I take action 1, I'm going to stay in state S2. But if I take action 0, I'm going to move from state 2 to state S1. So if we look graphically over here at the FSM, we can see that this is actually happening. So if I'm in state 1, I stay at state 1 if I take action 1. Similarly, I stay at state 2 if I take action 1. So we can look here, and it basically just says, If you take action 1, stay in the same state. If you take action 0, move to the other state, right? So this is the simplest possible way of representing states and state transitions. However, in general, it's much more complex than this, right? We've got a game engine like League of Legends that's running in the background that has very complex state transitions. Or maybe I've got atoms and molecules in the real world that robots have to deal with, right? So state transitions can be extremely complex, but we'll be dealing with pretty simple versions of those in this course. So the state transition function, the STF, in this case, the state transition function is a lookup table, right? It just says, if you're in this state and you take this action, go to this other state. So the simplest possible way to do a state transition function, or STF, is with this like table. It could be a successor function. So for example, if you're playing checkers and you move a piece to another place on the board, you've got some function that implements the game rules. Maybe if you're talking about like doing something like a shortest path pathfinding, you've got a graph that represents the environment, right? But the important part here is for our terminology going forward, we've got a state S and an action A. And S prime is the next state. So the next state is S prime, and S prime is equal to the application of the state transition function at the current state with the current action. So we're going to have some function that takes in the state, S, and the action A. Let's call that STF, and it's going to return the next state. Okay, so that's how we're going to do this in a game. So for example here, in Connect 4, here's a Connect 4 board. On the left, if I take the action, let's say yellow is the current piece to move. If I take the action of putting my piece down here, it's going to slide all the way to the bottom, and then that's my S, that's my action, and then this is my S prime. Okay? And this will actually be assignment 3. You'll be writing an AI to play Connect 4, so that's pretty cool. Similarly, in a game of chess, an action will be like taking a chess piece and putting it on a different part of the board. If you're playing video games, then of course you've got some sort of controller input, right? So here we're playing Street Fighter, and you've got an arcade stick, and every input that your fingers make, right? They pressing a button or moving the stick is going to cause some electrical signal to input an action into the game engine, and that's our action in that case. Here we've got someone playing StarCraft showing off their APM, right? So hundreds and hundreds of actions per minute in StarCraft. Or we could have like, you know, some person actually going outside and getting exercise in the real world doing actions, but we're not one of those people, right? But actions, basically anything that impacts the environment in any way. Okie dokie. Next, we have policies. So a policy is a map from states to actions, okay? What I mean by a map is, again, some sort of function. A policy takes as input a state, and it returns the action that the agent should do at that state. So this is supposed to be the pi symbol, but PowerPoint's font is a bit weird. So we have a policy pi, and we have an optimal policy pi star. Okay, so where you see a star, that means it's the optimal policy. So we can have some policy, any policy, let's say do random things all of the time. Or we could have the optimal policy, and we're going to represent the optimal policy by pi star going forward. So you can think of pi as a function, okay? And that function takes as input a state and returns an action. So given that we are in state S, do action A. And the policy, again, can be implemented as a bunch of different things. It could be a simple lookup table. It could be a bunch of if statements. So for example, maybe you want a simple NPC in a side-scrolling platform game. And so you say, if the player is to my left, move to my left. If the player is on the same horizontal row, shoot the player, right? It could be some arbitrary function calculation that uses differential equations or a neural network or something like that. So the policy is going to be anything that can take in a state and return an action. In this course, we're going to be looking at tabular policies, okay? For the most part, we're looking at tabular policies. And what a tabular policy is essentially a policy that can fit in a table that we can visualize for ease of use in this course. So for example, and this is a screenshot from our last assignment in the course, which is grid pathfinding. And in this example, we've got an agent here currently at this location, the red dot, and it's trying to get to these locations of high reward. And so what you see here is a policy table showing that if the agent is in, say, for example, this tile, then it should move to the left to get to one of these green tiles as quickly as possible. If the agent is here, it should move down. If the agent is here, this is a really cool example actually, because the agent can move up, down, left, or right, and it's getting equally as close to a green location. So a policy might be deterministic and say 100% of the time go left, or it might be stochastic and say, well, here we don't care where you go because you're going equally close to a goal. So 1/4 of the time go in a random, in any direction, right? So kind of just take a random action. But this is an example of a policy. Here's another example of a policy. Who out there knows how to play blackjack? Okay, so an example of a tabular policy for blackjack. Well, how is the table arranged in blackjack? So on the column over here, we've got your cards, right? And so this is like the current sum of your cards. And on the top here, it's partly cut off by my face, is the dealer's card that's showing. And so what this is, it's a table of values that says, okay, let's say I have a pair of 9s, and I want to know what to do if the dealer is showing an 8. Okay, so I would look, okay, I have a pair of 9s, the dealer is showing an 8, so I go across here, and if I have a pair of 9s and the dealer is showing an 8, then I should split. So that's the action that I should take. So this is another example of a tabular policy. We could also have a flowchart policy, right? So flowcharts are policies. So for example, I really like this policy over here when it comes to how to deal if you're a person who worries a lot, right? This is a policy on how to deal with your worry. Okay, so you start up here. Do you have a problem? No. Then don't worry. You're done, right? Do you have a problem? Okay, yes, I do have a problem. Can you do something about that problem? If you can't do something about the problem, then there's no reason to worry, right? And if you can do something about the problem, then you don't need to worry either. So don't worry. That's, so don't worry, be happy, that sort of thing. So that's just a joke, but obviously worry and anxiety are real things. But so what I'm trying to show here is that it doesn't have to be a table. This is essentially a bunch of if statements, right? So if statements in your code could be a flowchart if you want to put it up graphically. And there's all sorts, like a neural network can be a policy as well, right? So, but we're not going to go into every possible example. Rationality. Okay, you've heard of people being rational in real life or irrational in real life. You've heard the concept of rational numbers and irrational numbers. Throw out all of that, okay? When it comes to artificial intelligence and agents, rationality means something else. A rational agent is one that does the optimal action for every possible state, okay? So what is an optimal action? Well, it's the one that makes the agent most successful. So if we're talking about an agent that plays StarCraft, the optimal action is the one that helps it win, right? But a rational agent is the one that does the optimal action for each possible state, given what it knows. Okay, maybe there's important information it doesn't know. It's not omniscient, right? But given what it knows, it takes the optimal action. So what makes an agent successful? Well, that depends on the environment. It depends on the problem. So what we have to do is we have to define a performance measure. And a performance measure is essentially what we come up with to measure how successful the agent has been in a particular problem. And so rational agents have an optimal policy, okay? And it's optimal within its level of knowledge, meaning that a rational agent will be the most successful within a given performance measure. So the performance measure is the criteria for success of an agent. And it can also be called an evaluation function in some places. So here's a typical scenario. We're going to place an agent in an environment. Then an agent is going to go through a sequence of actions. The actions cause the environment to go through a sequence of states. And if the sequence of states is somehow desirable, the agent has performed well, and so the performance measure goes up, or the evaluation is higher. Okay? And then the process repeats and repeats and repeats. So as people wanting to implement AI in particular problems, here's one of the hardest problems about AI. It's coming up with a performance measure. Essentially, every single currently known artificial intelligence method, all it does is minimizes or maximizes a performance measure. Okay? So you've got to come up with typically one number, one floating point number that you want to be as large or as small as possible. And so, for example, we may have cases where that's really easy to determine. So you have a game like Flappy Bird. Well, the performance measure in Flappy Bird is really easy. It's how far to the right did you get, right? Other cases, it starts to get a little bit harder. We might have the shortest possible path between a start and a goal in a given environment, right? So our performance measure there goes up as the path length goes down. When we go back to the pole cart balancing problem, well, our performance measure here might be what percentage of the time is the pole being balanced? Or maybe how many seconds in a row can we have the pole being balanced? Our performance measure in games typically is win the game, right? Oh, I just lost the game. It's been so long. If you know what that means, I'm sorry. Okay, I won't go into it here. But yeah, performance measure, win the game. So, sorry, I'm getting a lot of angry messages from the chat now. But yeah, win the game of StarCraft. Destroy your enemy buildings. Win the game of chess. Put the other person in checkmate, okay? Win the game. So, rationality then depends on 4 things. God, what a great exam question this would be. So, it depends on the performance measure that defines success. It depends on the agent's prior knowledge of the environment, the actions that the agent can perform, and the agent's percept sequence up to date. Okay, so that's what rationality depends on. I mentioned this word before. Rationality is not omniscient. Okay, omniscience is like God, if you believe in one, right? They can see everything, no matter what. So an omniscient agent would know the exact outcome of actions. So, for example, if I am going to swing my sword in League of Legends, am I going to get a critical hit? Well, if I knew that, that would be great. Omniscient agents know the outcomes of actions. They know the outcome of randomness. So, for example, if you know what card you're going to be dealt in blackjack, the game becomes very, very different, right? If I know I'm going to get a 2 when I have a 19, well, I'm going to hit. But you would never hit on 19 if you don't know the actions, right? Or the outcome of randomness. Maybe you know the roll of dice in Monopoly, right? And you also know the entire state of the environment. So back when we saw the example of Piglet firing that rocket into the Baron, if Piglet was omniscient, it would know the current hit points of the Baron, but it didn't, right? So here's an example. What if I bet you that I walk up to you on the street and I say, here's a die. If the die, a 6-sided die, if it rolls anywhere between 1 and 5, you win $100. If it's a 6, you lose $100. Would you take that bet? Right? Say in the chat, would you take the bet? I hope you would take the bet because, anyway, we'll get into this in the future. But essentially, you have a 5 out of 6 chance of doubling your money, and you have a 1 out of 6 chance you lose your money, right? And we're going to do a whole section on game theory and expected value, stuff like that. Well, we'll get into it. But let's say that a person takes the bet, but a 6 was rolled. Was the bet still rational? Yes, the bet was still rational. The reason it was rational is because the expected value of that bet was positive. Why wouldn't you take it? Now, if that's your last $100 in the world and you need it to feed your children, maybe you don't go do it. But factoring all that stuff out, if the only evaluation here is money, right, and not starvation of your children, then the bet is rational because you had such a high chance of winning. Now, this is something that gets to me, and it happens all the time in professional sports, is that even if there's a rational choice to make based on statistics, whatever, coaches are sometimes afraid of looking bad, right? They're afraid of the 6 being rolled. And so they'll go with something else, even though this other action is rational. And it happens a lot of the time in the other way, where someone takes this Hail Mary pass when there was a safer option, and if they drop the ball, they're a loser and everyone hates them. And if they catch the ball, they're a hero and everyone loves them. If you get anything out of this course, please take the following. Judge an action by its expected value and not by its outcome, okay? Whether or not you lose or win the lottery, buying a lottery ticket is still stupid because the expected value is so little, okay? Even if you go out and you play a slot machine and you win, it was still dumb to play the slot machine because your expected value was so low. It's a bad idea to go play blackjack because the house is going to win over time, right? So please, in life, try and judge rationality by the expected outcome of an action and not the actual outcome of an action, and you'll lead a much happier life. Trust me. All right. Philosophy aside, we're moving on to environments now. So this is all just explaining that rationality is within what the agent knows about the environment. It's not omniscient, right? So an omniscient agent would have known the dice was going to be a 6, and it wouldn't have taken the bet. But a rational agent doesn't know its outcome, but it says, oh my God, I got such a high chance that you should take the bet. Okay. This stream, for legal purposes, I am not giving gambling advice, so don't come to me when you lose your $100. All right, environments. We talked about this a little bit, but what is an environment? Essentially, a given task in an environment defines the problem that you're trying to solve. And the rational agent is the optimal solution to that problem. So the specifications and properties of an environment are going to greatly impact the design of a rational agent to act within that environment, right? And remember that a state is a particular configuration of a given environment, okay? So here we have an environment of chess. So the environment of chess contains the rules and the boundaries. So for example, over here we have an 8x8 board and we have the pieces, right? So these are the things which can live in a chess environment. We also have the rules, so the king can only move 1 in any direction, queen can move all in any direction, etc., etc. The legal actions, so I just explained that a little bit, like pawns can take by moving diagonal, you can castle, like all the actions that are taken. And you also have a starting state of the environment. So you line your pawns up on the second row, your other pieces in a specific order on the back row, right? If you have a game of StarCraft, you're going to start with a few workers and a mineral patch and all this kind of stuff. And also in the problem, you're going to define your goal conditions or your goal states or the performance measure that you're trying to maximize, right? So that is an environment. The environment contains all of this. So an example state of the environment of chess is this is the starting state of chess over here on the left. Over here on the right is like a typical mid-game for a game of chess, right? And so the agent can observe the entire environment of the game of chess, okay? So, agent, observations, and state. For the agent, the state of the environment is based on an observation that it can make. So that observation may not be a complete representation of the environment state, right? There might be other things we saw before that the agent can't perceive from the environment. And again, chess would have something like castling. So maybe if we want the chess state to be complete, we could say, okay, you have a flag here that says whether or not you've castled, something like that. So the agent's observation is all that it can use to make a decision, all right? So that's the difference between an environment and the agent's observation and the agent's perceived state of an environment. So for an example, let's take the environment of driving, okay? So you're out in the real world. You've got this huge city. Maybe I'm like right here somewhere. Let me see if I can get the pen out. So maybe I'm like right here in the environment at this red dot. Now, maybe there's I can't see if I'm coming up, okay, these are going in the wrong direction. Maybe I want to take this turn off down here, but I can't see that there's a truck coming this way or something like that. Or maybe, there's a car coming behind me doing 100 miles an hour or something like that. So the environment contains things that I may not be able to see. When the agent is actually driving, though, it does have a state of the environment that it can currently observe. So here we have an agent. This car is the agent. And what you see here, maybe it has a camera, maybe it has some laser range finding and some object detection and line detection and stuff like that. And you're looking at sort of the play-by-play of the state of the environment. As you can see, it's missing a bunch of stuff. It's missing all the buildings over here, maybe. Maybe it's missing some pedestrians. It's missing the trees, for example, that you can see down here. But this is just a representation of the state that it can see, which may not be the entire environment. So I'm just trying to drive home that point because it's very important when you're working in AI. All right. Another thing, state and action spaces. So the state space of an environment is the number of possible configurations of the environment for a given problem. And the action space is the number of actions that are possible from a state given an average or worst case complexity, right? And usually we're going to, we use state space and action space as an estimation of the complexity of a problem. And what I mean by complexity here is sort of like big O notation, right? So if you've learned that the algorithmic complexity to solve a problem sometimes, and I'll give an example shortly where it doesn't happen, but if it has a very large state space and a very large action space, it's very likely that the problem is hard. So let's look at a couple of examples of state and action spaces. So here, and this is from a really great website. It's going to be linked up on the top right. It's hidden by my face right now, but it's in the slides. Let's look at the state space. This is an animation, so I'm continuously reloading it. Let's look at the state space of tic-tac-toe. Okay? So, tic-tac-toe, state space complexity. Every place on the board could either be an X or an O or a blank. We've got 9 places. So, if each of 9 places could have one of 3 possible values, then we have 3 to the 9 is approximately 10 to the power of 4 as the number of possible states of a tic-tac-toe board. Now, that doesn't include transpositions and states that are rotationally symmetric and stuff like that, but it's a rough estimate of the state space of the board. And why does that matter? Well, let's look at this. If we have 10 to the power of 4, so around 10,000 possible states of an environment, then we know, well, can computers do 10,000 operations very easily? Yes, right? So we can look at the game of tic-tac-toe, and just by saying, okay, well, there's 10 to the 4 possible state spaces, or possible states it can be in, I can really easily enumerate all of those states. So if I can exhaustively enumerate every possible state, then solving the game becomes trivial, right? So if the state space is this small that a computer can do it in less than a second, then it's not a very interesting problem from AI point of view. Let's look at chess as another example. So in chess, you've got 64 places on the board. You've got 32 empty board spaces. You've got 8 pawns in 2 different sets of 2 players, 2 pieces in 6 different sets. And so this is how you would calculate the state space of chess, which is about 10 to the power of 43. And I'll visualize for you in a minute just how big that number is. But needless to say, we can't enumerate every possible state of chess. However, we can do it for checkers, and it's been done for checkers, which is kind of fun. Let's look at Go. So Go is even bigger. So we've got every space on the board could be a white, a black, or a blank. So each possible state could have 3 spaces. 19 by 19 is 361. 3 to the power of 361 is approximately 10 to the power of 172. Okay? That's a really big number. So if we look at the state space complexity of these games, we have tic-tac-toe with about 10,000 board states. Whatever this number is, why even give it a name at this point? 10 to the power of 43 for chess, 10 to the power of 172 for Go. Now, here's an even bigger number. This is the game tree complexity of chess. And we'll talk about trees and algorithms that operate on trees very soon. But what the game tree complexity, whereas the state space complexity is how many configurations are there of a board, the game tree complexity is how many different possible ways could a game play out, right? And so these numbers are far bigger because the number of possible histories of a game of chess and the number of possible ways you could get to all possible states is way bigger than just the number of possible states. And the reason for that is that you can get to the same state in many, many, many different ways, okay? So these numbers go way up. So we couldn't possibly exhaustively search all these, and I'll show you why we can't possibly observe all these. All right. So the number of seconds in a century is 10 to the 9. All right, so this is 10 to the power of this number. The number of humans that have ever been born, 10 to the 11. The age of the universe in seconds is 10 to the 17. The diameter of the universe in meters, 26. The number of stars in the universe is 30. Okay, now we're getting ridiculous. The number of atoms in the universe is 80. The number of protons to fill all observable space that we know of is 122. And the game tree complexity of Go is like way bigger than that, okay? So if the whole universe was filled with protons and every proton had the fastest supercomputer known to man, it still would not run in time. I'm sorry if there's a helicopter flying by if it's loud. It still would not run in time of the number of seconds of the universe, right? So we can't possibly enumerate all possible states of Go. Now, StarCraft, I can give you in one of the papers that I wrote, because my PhD was on StarCraft AI, it's way bigger than Go. Way, way bigger than Go. A very, very ultra-conservative lower bound is 10 to the 1,000, okay? So, however, a really important thing to realize is that a large state space does not prove that a game is complex. All it proves is that we can't enumerate it, okay? Exhaustively enumerate it. So what state and action space analysis does is it shows us that a game, it can prove that a game is simple, right? So if I've got a game or an environment with, say, up to a couple of billion states, then I can reasonably exhaustively enumerate all of those states, right? Because computers are fast. So tic-tac-toe, 10,000 states, super simple game. So it can prove that a game is simple, but it can't prove that a game is complex. Why is that? Well, think about the game of Go, okay? So Go is a super complex game. However, let's modify one rule in Go. So I'm not going to go over all the rules of Go, but essentially you place a stone, I'll place a black stone, you place a white stone. I'll place a black stone, you place a white stone. And then if you surround your opponent, you capture their stones, and the winner of the game of Go is whoever has the most stones left at the end. But let's modify Go so that you no longer capture stones. Okay? That's interesting. There's an odd number of spaces on the board. So that means that if you can't capture any stones, all you do in this modified game of Go is place pieces. I place one, you place one, back and forth until the whole board is full. And once the board is full, who has the most pieces? Well, it's whoever placed the stone first, right? And so even though this new modified version of Go has the exact same state and action space complexities of the original, actually complex version of Go, it's a trivial game because the optimal action is just place a stone on the board. And we know who the winner is going to be from the outset. Okay? So it doesn't prove that a game is complex, but it shows that we can't enumerate all possible states. All right, so that's what I just said. So it can do things like prove that tic-tac-toe is easy, but it can't prove that a game is hard. Alrighty. So let's recap just a little bit about environments. So environments, the definition of an environment, if you want to define an environment and give it to someone, for example, if I want to hire a programmer to create the environment for me in a game, what do I have to give them as the definition of the environment? So the definition of environment has to include the rules or dynamics that govern it. So for example, are there physics? Is there gravity? The game rules of a chessboard or a Go board, etc. The legal actions that are allowed at any state. So for example, in a pathfinding example, maybe I can't move past the wall or something like that. And I also have to give the initial and the goal states that I start in and that I want to end in. And that's usually given by the problem instance. Okay. For the rest of the lecture, we're going to go into the properties of environments that make them different. And we're going to see that based on specific properties of environments, we're going to be able to use or not use specific algorithms to try and solve those problems. Okay, so let's get into those properties now. And these properties are going to be a question on the exam. They just are going to be a question. So make sure you know what these properties are. The first property is the observability of the game. Okay, so fully observable versus partially observable. In a fully observable environment, the agent's sensors, whether it's my eyes or the RAM or whatever, they give it access to the complete state of the environment at any given time. So you have access to all of the relevant information of a state to make an optimal action. And when you're talking about games, fully observable games are called perfect information games. You have all of the information that you could want. In partially observable games, some of the data or some of the environment is either hidden or occluded from your view. In the real world, your sensors may be noisy, right? Maybe you don't have the exact distance between you and the car in front of you, so that's partially observable. And in games, these are called imperfect information games. Okay, so on an exam, maybe I'll ask you to define what an imperfect information game is. Or I'll ask you, which of these games is fully observable, which of these games is partially observable? So obviously with the caveat of castling or whatever, chess is a fully observable game, and StarCraft is a partially observable game. Why is StarCraft partially observable? It's because we start the game only being able to see our units. Maybe we know what map we're on, but we may not know where our opponent is or what units they're making because there's this fog of war that's surrounding them, right? So StarCraft and a lot of competitive video games are going to be partially observable. Answer in the chat if you think Counter-Strike is a fully or partially observable game. And I'll keep going, and I'll come back and look at the answers. Deterministic versus stochastic. Okay, everyone said partially. Why is Counter-Strike partially observable? Because you don't know where the enemy is, right? Perfect. Also, someone says, what about wall hacks? You still don't know their ammo, right? So there you go. So it's still partially observable. Okay, a deterministic environment means that the next state of the environment is entirely determined by the current state and the action of the agent. There is no randomness in the environment. So, like, if I take this action at this state, I am 100% guaranteed to be at this next state, right? That's not true for all environments. Some environments are stochastic, which means there is uncertainty about the outcome of an action. So there might be some random chance. There might be a dice roll. There might be a card draw. So in blackjack, is blackjack deterministic or stochastic? Well, when I choose hit me, I don't know what my next state will be, right? So that's a stochastic environment. And so there is some sort of random nature to the environment that affects the next state of the environment when I take an action. And so you think about it from the point of view of the agent, right? If the agent doesn't know what's coming next, then it's a stochastic environment, right? So, we could get into the age-old debate of whether or not the universe is actually random or if it's deterministic. But let's just pretend that randomness actually exists in some form. Pseudo-randomness is fine for our games, right? So that's what I'm talking about. I'm not getting into the philosophical debate about what true randomness is. It's the uncertainty of an agent about the outcome of an action. So here again, chess, 100% deterministic. It would be really cool to play a non-deterministic version of chess. Maybe I have like a 10% chance to be captured instead of capturing, right? That would be a cool version of chess. Maybe you have to roll dice like Dungeons and Dragons. See if you get a crit, right? And take 2 pieces instead of 1. I don't know. But chess is deterministic. A stochastic game would be something like poker, where you get dealt cards, right? And there's randomness in the shuffling of the deck. Next is episodic versus sequential. Turns out most games are sequential, or most environments are sequential, but let's look at the difference between these. In an episodic task, an agent's experience and actions can be divided into atomic episodes. So an agent perceives the current state and takes an action. The next episode does not depend on the previous episode. And you might ask, what kind of environment does that? Well, we'll see in a bit. A sequential environment, the current action will influence future decisions. And actions may have long-term consequences. Okay? So, one example of an episodic task is optical character recognition, for example. So we want to know which digit is this. Well, which digit the last one was doesn't influence our decision on which digit the next one is. Okay, so that's an episodic task. Our decision on what to take an action or how to determine what this character is completely episodic. You can understand that sort of thing now. But most environments are sequential in nature, where the action that we take, if I move up, well, now I'm up. Right? So my next action will depend on the new place that I'm in. If I capture a queen, now that person has no queen left, so they can't take anything with a queen. They can't move their queen. So that's a sequential environment. The next property is dynamic versus static. In a dynamic environment, the environment may change while the agent is making a decision. So in a dynamic environment, it's sort of continuously asking the agent what to do. What are you going to do? What are you going to do? What are you going to do? And it can always take actions. In a static environment, the environment only changes when the agent takes an action. And so decision-making time doesn't really matter, okay? So in games, if you were looking at this from a game's point of view, a dynamic environment is a real-time game, and a static environment is a turn-based game. Okay, some turn-based games do have timers like chess if you have a clock, but let's just throw that out the window for a bit. And so, for example, in StarCraft, it's a dynamic environment. It's a real-time game. So if I just sit there in StarCraft or in Counter-Strike, someone's going to shoot me in the face, right? It doesn't care how long I take to make decisions. I'm just a noob, and I'm going to get hit. If I'm out in a self-driving car, cars are going by me, right? That wall is coming toward me. It doesn't care if I make a decision or not, right? So it's a dynamic environment. In a static environment, the environment is just sitting there waiting for you to make a decision. Please move a piece eventually. Okay, I'll come back in an hour, see if you moved a piece, right? So that's like a board game like checkers or Go or chess. Next property is discrete versus continuous. And this distinction is applied to the state of the environment. So it determines the way, essentially, that time is handled. Okay. So in a discrete environment, there are a finite number of distinct states. So there is a discrete set of percepts and actions. So we'll talk about the distinction in a second, but in a continuous game or a continuous environment, there is continuous time and continuous actions. Okay, so for example, in poker, maybe I make a bet. That's an action. That's a discrete action. In chess, I move a piece. That is a discrete action. Versus in some environments, there is a continuous time. Now, again, this is sort of a philosophical debate. Is in the reality that we perceive, is time discrete or is it continuous? Are we living in a simulation? All that kind of stuff. Let's just say that physicists yet haven't got to the level where they can say that it's discrete. So we're going to assume the real world is continuous. So continuous meaning I can take actions that have durations, and those durations can be like any floating point value, etc. I can have my hand up here for a specific amount of time rather than discrete time ticks like you would have in a video game engine. And a distinction here is that sometimes, like a game like StarCraft or Counter-Strike is a discrete simulation. Like there is obviously one tick of physics update, one tick of rendering, that sort of thing. However, in some cases, you may want to consider them as continuous because they're continuous enough. Okay, I won't ask you on an exam whether or not Counter-Strike is discrete or continuous because but I will ask you, like, you know, is chess, is driving cars and stuff like that. Okay, single agent versus multi-agent. In a single agent game, there's only one agent acting at a time, and it is trying to maximize its own reward. So for example, maybe we're trying to solve a puzzle like a Sudoku, right? Or a crossword puzzle. Or pathfinding. So Google Maps is trying to say, here's the fastest path from here to here. It's a single agent problem. In a multi-agent problem, or in a multi-agent environment, you have multiple agents that are acting together. And they could be either cooperative or competitive. So let's look at this. In a single agent environment, let's say we have pathfinding over here. So this is just a little GIF, an animation of people placing obstacles, and your single agent is trying to get from blue to red as fast as possible, so it's showing you the shortest path between those 2 points. There are no other agents here trying to get in your way or steal your hit points or whatever. In League of Legends, it's definitely a multi-agent game. League of Legends is cool, or other MOBAs are cool, because it's cooperative and competitive. You've got 5 people per team, Counter-Strike, 5 people per team trying to cooperate to beat the other 5 people, right? And so obviously the real world is multi-agent, even if we don't think so. Even if you're working on single agent problems, like a bird might fly into your forehead or something, right? Okay. Complete versus incomplete information. Now, before we had perfect versus imperfect, complete versus incomplete is different. So in a complete information game, all of the game rules and physics are known, and all of the possible actions are known. In an incomplete information game, the game rules or physics may not be known to you. The actions may have to be discovered as you go along. I remember playing this one game, a card game called Mao, I think it was. And this was like 20 years ago, a long time, where if you'd never played before, so the way the game works is that there's a base set of rules. It's a card game where you lay cards down on a table, you draw cards, etc. So there's a base set of rules, like if someone, you have to pick up a card and you have to lay it on your turn. But as you're going, you can make up rules, and you don't have to tell other people the rules, and they have to figure out the rules as it goes. So an example might be like if someone plays a jack, you have to say, hello. And then, so what you do is like when you play a jack, you say hello. And if people don't, they have to draw cards or something. It was really weird. But the point being, there are games in which you do not necessarily know all the rules, right? Maybe the real world. If you have a robot, you don't necessarily know all the rules of the real world. You have you may be trying out things. Like, let's see if I apply voltage to this arm, what happens, right? A lot of reinforcement learning, machine learning. You may not know the actual rules of physics or of your environment before you try and machine learn a task, right? So complete versus incomplete information is also a big deal. So here's some example game environments using all of our properties. And I'm sort of going here from like least complex up to most complex in terms of the properties, okay? So we've got a crossword puzzle. So a crossword puzzle is sequential because as you fill things out, it matters. It's a single agent, deterministic, fully observable, static, discrete environment, okay? Chess, it's a sequential game again, but now you've got multiple agents. So I'm fighting against you, right? Again, the rest of the properties are the same. If you take chess and add randomness, now you've got something like backgammon. So backgammon adds a stochastic nature to the sequential multi-agent problem. Backgammon, however, is fully observable. Let's add partial observability to backgammon, and now we get something like poker, right? Because you don't know what the other people have in their hands. But poker is still a static game. Let's change it to a dynamic game. And now we've got something like StarCraft, which is sequential, multi-agent. It's got randomness. It's got partial observability. It's got dynamic. StarCraft has a little bit of randomness, like the outcomes of actions are actually a little bit random. So it's just a more difficult environment to solve problems in. But it's still discrete, right? Because it's a video game. So the real world, you add in continuous time, and now you've got like all the hardest possible properties. And so this sort of thing, I could ask you on an exam, what are the properties of backgammon? And I'd give you like episodic, agents, deterministic. Or I could say, name for me a sequential, multi-agent, deterministic, fully observable, static, discrete game that wasn't listed in our slides. Something like that. So that's just something to think about for exams. Okay. And that is the last slide of today. And I think we ended right on time, which is awesome. Great. Okay, let's go back really quickly to explain again. So the next lecture we're going to be talking about problem solving and search. Search is going to be really important. It's going to be what assignment 1 and 2 are on. And again, next class, that lecture is going to go long, okay? It's probably going to be about 2 hours. And the reason I'm able to do that, A, because it's online, but B, is because the following lecture is like an assignment 1 help and tutorial stream all out, okay? So assignment 1 is pretty simple. It's breadth first search and depth first search. Assignment 1 is really, here's getting used to my assignments and like getting used to JavaScript, getting used to arrays and for loops and classes and stuff like that in JavaScript. So that's going to be the next lecture, and I will see you for that one next time.